Hello and welcome to Lecture 13 of Introduction to Computational Literary Analysis. And today we're going to look at Corpora again, and we're going to introduce the library Scikit-Learn. All right, here we go. Okay, so I've just opened up a new notebook and I've called it Corpora and Scikit-Learn. I'm going to import the NLTK because there are some libraries. There are some corpora here that in this library that could be interesting to us. So nltk.corpus.gutenberg is one of them. And yeah, why don't we just see what it looks like? We can do things like we can look at the contextual help for this. And what does it tell us that we could do? Okay, so it says that we can get the root directory. It says that we can get file IDs. There are a couple of tokenizers there for some reason. Okay, but the one that we want is file IDs. So if we run file IDs here, it shows us that these are all of the files that are contained in this corpus. So we have Jane Austen's novel Emma, her novel Persuasion, her novel Sense and Sensibility, a copy of the King James Version of the Bible, poems by William Blake, and so on and so forth. We have 3 Shakespeare plays, and we have Whitman's Leaves of Grass. Okay, so we can use these file IDs to get the texts out of this. Okay, so the same methods work as before. So there's the raw method, and we can give it file IDs, and we can get the raw text as a single string. And we also have the words method, which gives us just a list of the words. So in other words, this is already, it's already tokenized. You know, and if we wanted to, of course, we could tokenize it ourselves using a different tokenizer or our own method. But, you know, it might help to get the words here because it's already, the work of tokenization has already been done for us. So, yeah, why don't we look at Whitman's Leaves of Grass. So you can see down here that it takes a list of file IDs as a parameter. So what if we give it just one file ID, Whitman Leaves text? Okay, great. It returns a list of all of the words, it looks like. Leaves of Grass by Walt Whitman. Yeah, why don't we call this Whitman Words? And let's get the length of that. Great, 154,000 words there. Why don't we take a peek at it somewhere in the middle, like word 250 to word 300. Yep, that's certainly Whitman we're listening to there. Okay, great. So as you can see, you know, if you can do it once, you can generalize this to do it with everything too. So what I can do is I can write a little for loop or a little list comprehension that goes through each of the file IDs and gets their words. You know, so I can make this a dictionary if I want, and I can call it file ID in words, but yeah, actually I'm going to get the words. For that file ID, for every file ID in nltk.corpus.gutenberg.fileIDs. Okay, so what this will do is return a dictionary where the key is the file ID, in other words, this file name like Shakespeare Hamlet. And the value is just, it's going to be the words there. It's going to be like all of the tokens for that text. All right, so yeah, what should we call this? Gutenberg dict. Now, let's see if this behaves the way, let's test this to make sure it behaves the way that we expect it to. So Gutenberg dict, if we index it by Whitman leaves, this should give us the full text of Whitman in tokens. So if we were to take the length of that, it should tell us that it's the same thing as this up here. Yeah, so we have successfully made this Gutenberg dict, and we can actually peek at all of these if we want, by saying, I can make this a list comprehension. And I can go through, I'm going to write this backwards. I go through each item in Gutenberg dict items. So that's going to give us the key and the value. The key and the value in this case is file ID and tokens. So I'm going to go through file ID and tokens for everything in Gutenberg dict items, and I'm going to show that file ID. Actually, I'm going to make this an F string. I'm going to show the file ID, and then I'm going to show just the first few tokens. So yeah, maybe the first 8. Now if I run that, this shows us the first 8 tokens of each one. So I can, this is just so I can verify that I know what's what. So this is Alice in Wonderland. There are 3 G.K. Chesterton novels. We have some children's stories. We have Moby Dick, the infamous Moby Dick. We have Paradise Lost, an epic poem by John Milton. Yeah, most of these have metadata sort of built in, which is kind of handy. So, we could extract that if we wanted to. We could say if we're interested in getting all of the Chesterton novels, we could either get all of the file IDs that start with Chesterton, or we could write something to sort of go in here and find the byline. So there are lots of ways that we could slice this data set. Why don't we get just a few more tokens? So the year is in almost all of these. Not the Bible, of course, because that's that's a story in and of itself. But we have years for just about all of these. So we could write another little list comprehension that extracts the year, just by going through all of these tokens and getting the first one that is just numeric. So save this real quick. Okay, yeah, so let's do some stuff with this text. Okay, so first thing that we probably are going to want to do is to lowercase everything again, so that we are treating, volume capital in all caps the same as volume, in lowercase. So it's a little bit more difficult now because we're dealing with tokens instead of a whole text, but that's no big deal. We'll just go through and write a for loop to go through all of them. All right. So we have Gutenberg dict. And what we want to do is go through each of the keys and each of the values of those keys. And for the value, we want to lowercase everything. So we could write this, I'll write this the long way first. We will create a new dictionary, and so for that file ID and for the tokens in Gutenberg dict items, and again, items is going to go through each one of these and give us file ID and the value, the key and the value for all of those. And it's going to assign it to the variables file ID and tokens. I could say lowered tokens is, and here I'm going to write a list comprehension, token lower for token in tokens. And if I wanted to, I could also do other things here, like remove punctuation or something if I wanted to. And now I can add this to my new dictionary. Gutenberg lowered file ID is lowered tokens. So yeah, this is taking a long time. So I'm going to copy and paste what I wrote up there for peeking at everything, and I'm just going to change this to Gutenberg lowered. So yeah, that's exactly what we wanted. We wanted everything in this lowercase. Another way that I could have written this as well, if I wanted to do it the short way, is write a list comprehension within a dictionary comprehension. So I'm saying I want my dictionary to look like file ID and token lower for token and tokens for each file ID and tokens in Gutenberg dict. Right. Gutenberg dict items. And this is going to do the same thing. So if we look at this, it should show us the same thing. And here's a neat trick. If you have a comprehension like this, you can actually insert a line break, and it just makes it a little bit more readable, and Python treats it just the same. All right, so now we have lowercase tokens. So one thing that we could do is we could use a counter here, but we could also use frequency distribution from NLTK, and that does the same thing, but just gives us a few extra methods that could be useful. So I want to run this frequency distribution on. You can see down here it takes what it calls samples, but those are really going to be tokens. So that's the kind of thing that we want to do, and we're going to run that on file ID and tokens in Gutenberg lowered items. And we'll make this into a new dictionary where I have file ID and the frequency distribution of all of those tokens. And I can call this Gutenberg frequencies. All this does is just run a frequency distribution on each of the collections of tokens from each of these. So I'm basically just generalizing something where I could do NLTK frequency distribution on some tokens. So let's say, for example, that I got Whitman tokens. So Whitman words is something that I already have here. If I were to run that frequency distribution on Whitman words, I can call this Whitman frequencies. Let's look at that. So if I just get a preview, it shows me that he uses the comma the most. Then the word the, and then and then of, and then I, just all kinds of common things, I suppose. What other things can we do with this frequency distribution? We can get the hapax legomena, which are, again, words that are only used once. This is often pretty interesting. Yeah, you can totally hear Whitman here. Deathless. It's a great word. Densities. Now you see what this, you can tell here that it hasn't been lowercased, so we would have to have first have done something like this. Lowercase everything, and instead of doing Whitman words, we would do Whitman lowered. Yeah, and then this gives us a little bit of a different view. Spectroscope. Amazing. Does he use... Oh, I thought that said internet, but it's actually an interpret. Be like, damn, Whitman, 1855. Yeah, so just like in counter, we can get the most common. So, we could look at the most common 10 words. Oops, I indented it. Yeah, what else can we do? We can get... We can tabulate this. It's a little messy looking. tprint is just a string representation, so this is kind of just peeking at the frequency distribution. Yeah, so anyway, that's pretty neat. But yeah, what we've just done is we've taken the frequency distribution of every text in our corpus. So that's pretty great because now because this is a dictionary, we have kind of the perfect format for bringing this into pandas. So I'm going to come up here and import pandas as PD, as usual. And now that I'm down here, I can do PD data frame and give it Gutenberg frequencies. And because the frequency distribution is dictionary-like, I expect this to work just kind of magically. And I say magically because, Pandas has figured out that because we have a dictionary of dictionaries, we have first the text name, and then we have a frequency distribution which is dictionary-like. It's figured out that what we have is two-dimensional data, and it's done the work of saying, okay, well, does the word Emma occur in Austen's Sense and Sensibility? No, it doesn't. Does it occur in William Blake's poems? And this actually, solves a huge problem for us. Anyway, now we can compare lots and lots of words across lots of texts. So it's super useful. So I'm going to rename this, and I'm going to call it like Gutenberg DF, which is what Pandas normally calls like a data frame. Great. So Gutenberg DF, I can do something like I can get the loc, which is the way to access a row. And why don't we compare the use of, say, like a male pronoun. So these are the raw counts. So already we know that we're more interested not in the counts but the frequencies adjusted for the length of each text. So one thing that we could do is we could use these word lists up here. So this is Gutenberg lowered. And yeah, we can just get the length of each text this way. So again, we can go through the items. And I want to get file ID and the length of the words for each file ID and words in those items. Great, so now I have a list of all of the words. Yeah, I can already see it at a glance that the Bible has 1 million something words, which is a whole lot. I can plot this if I want to, just by, first I have to put this in a pandas series. And I'll make this a bar chart. Yeah, and just as I thought the Bible is way off the charts in terms of its length, and Blake is very, very few words, which makes sense because it's just a group of poems, and it's not like really verbose work like Whitman's Leaves of Grass. And we could make this a little bit more readable if we wanted to, by doing something like that. Yeah, anyway, if we don't plot this, Actually, you know what? I'll keep this in the notes that way. And then I'll paste it down here because I want to take this thing, this series, and assign it to some variable like Gutenberg lengths. You know, because if I have that as a series, and if I have the frequency distributions as a series, then I can adjust for each. I can adjust for each of these. Yeah, so I have this data frame, Gutenberg DF. Let's look at what that looks like again. So because all of these are columns, and because this Gutenberg lengths is the same number of columns, this has a length 18, and this has 18 columns, pandas will be able to figure out that if I divide one by the other, that what I actually want to do is divide that by the columns. And yeah, has this done what I want it to do? It should have divided everything by the total number of words in each of the texts, therefore giving us the percentages rather than the raw counts. And yeah, that's pretty much what we want. So I can call this Gutenberg frequencies. The frequency distribution isn't actually frequencies, it's counts. Percentage, Gutenberg percentages data frame. We're getting kind of long names for things now. Okay, so another thing that I want to do again here is probably fill in the NaNs with 0. Great, and now we can compare words kind of more like we expect. So yeah, what if we look at him? Oh, that's right, because we have to do .loc. So these are the percentages of the word him. And again, we could put this into a pandas series and plot it as a bar chart. It's kind of hard for me to see the whole thing. But yeah, that's interesting. Gonna save this. Okay, yeah, so it surprises me that Whitman has a very low percentage of these, but I guess that shouldn't be too surprising if we think about them as genres. So, Whitman and Blake are both collections of poems, and so him sounds more like a dialogue word than anything else. So what about, and it's huge in the Bible for some reason, what about he? Okay, great. What about female pronouns? She. Yeah, so in a novel with female protagonists, and in Jane Austen's novels, she is much higher. It's super low in Moby Dick, of course, the seafaring tale in which there are very few women. Okay, yeah, what if we wanted to compare a few? We could give a list here if we wanted to. So, we're just adding square brackets. Yeah, let's walk this back. Yeah, okay, so we have a data frame here. Can we just plot this? Okay, so yeah, you can see that it's not really plotting this the way we would expect. Maybe as a bar chart it makes more sense. Okay, yeah, this is kind of hard to read, because we have this huge color coding here. So instead, yeah, why don't we transform this so that the columns are rows and the rows are columns. So to do that in pandas, we can do .t. Yeah, and here we can get like a better sense of female pronouns and male pronouns, and yeah, and who is using them and where. All right. So yeah, I want to show you a few, like a couple of neat tricks that we can do with a corpus like this if we have it in a pandas data frame. So one is, we've done this type token ratio function before. Let's write one that takes tokens and it returns the number of those tokens divided by the length of the set of those tokens. So this is our type token ratio function. And because we have Gutenberg df is all of our counts, actually we want this one instead. Gutenberg lowered. Yeah, I shouldn't have printed out that whole thing because that's going to be huge. Yeah, because we have this, I can run the type token ratio on each item in this dictionary. So I could say file ID type token ratio for the tokens for file ID and tokens in Gutenberg lowered items. So again, this is just a dictionary comprehension. Yeah, but maybe we want to compare only the same number of tokens in each. So what if we compare only the first 5,000 tokens? Great. And now, yeah, what if we put this into a pandas series and plot it as a bar chart? Wow, okay, so the Bible has the highest type token ratio. That's kind of interesting, but I guess it makes sense because there are a lot of these begats. We have whole chapters sort of devoted to genealogy, and they're just really lists of names, which are all unique tokens. But apart from that, who else has the highest vocabulary? I'm surprised that these children's stories are so high. If anyone's read that, by the way, tell me why, because that could be something interesting. And Shakespeare has a fairly high vocabulary, as we all know. Yeah, I wonder if it's that some of these have different lengths, and the length is kind of skewing things. What if we only look at the last words? So instead of looking at the first 4,000 tokens, we can look at the last 4,000 tokens. So minus 4,000 to the end. Okay, this is kind of a different picture now. Oh, you know what? I did it again. Yeah. Those are the types. And these are tokens. Yeah, I had it. No wonder that was so surprising. Yeah, I was doing token type ratio instead of type token ratio. This makes a lot more sense. Yeah, so here actually the Bible has the lowest. Yeah, that surprises me a little bit because of all of the begats. But again, we're looking at only the last 4,000 tokens, so that might have something to do with it. And here Whitman has the highest. Whitman does have a pretty amazing vocabulary, and he brings in lots of stuff. He has very, very specialized words. Yeah, what if we only look at the first 4,000 words? So here, Paradise Lost. So if you've read Paradise Lost, in the very beginning of Paradise Lost, we get this kind of list of demons. So probably that has something to do with it. And the lowest here remains the Bible. Yeah, what if we took like a middle 4,000 words, say from 4,000 to 8,000. Paradise Lost, again, is the winner here in type token ratio. So you can see, yeah, this is not always going to be super regular. It's not going to tell us the same story if we look at a different segment of the text. And that could be interesting. Maybe we want to compare all of the beginnings and all of the ends, in different categories. Okay, so we've done all of this stuff before, really, so most of this should be review. We're just using a new corpus to do it, and we're putting it in a dictionary. However, yeah, I want to show you the Scikit-Learn way of doing it. So I'm going to come up here and import Scikit-Learn, which is called sklearn, even though it's Scikit-Learn. So Scikit-Learn has so many modules. It's crazy. So yeah, I have to remember where this is. All right. Yeah, so Scikit-Learn has this feature extraction module, and inside that it has a text feature extraction module, and inside that it has a couple of very handy text mining tools that are kind of like these big super functions. And they are TF-IDF transformer, TF-IDF vectorizer, and count vectorizer. So count vectorizer is, yeah, one of the simplest ones. So we'll Yeah, why don't we look at that first? So count vectorizer, it can take different types of input. So by default, it takes content. So content, it calls strings. But it can also take file names, and it can also take files. So what this means is you can have the count vectorizer do the readings of files for you, which is a really useful feature. So then you don't actually have to open anything and read it. You can just pass it a list of file names. Yeah, so that's one thing that it can do. It uses Unicode by default. You can tell it to ignore errors. You can tell it to strip accents from things, and that's useful. So that transforms, accented E like cafe. It transforms that to calf, like this. You can tell it to lowercase words while you're at it. You can give it a custom preprocessor function of your own that you've written. You can give it a custom tokenizer function, but otherwise it's going to use its own built-in tokenizer, which is this regular expression that basically says, find anything surrounded with spaces or white space. And that's useful, but sometimes you want to use the NLTK tokenizer instead because it's a little bit more accurate. You can also tell it to get n-grams of a certain range, and by default it does unigrams, so it just handles words, but you can tell it to get unigrams, bigrams, and trigrams too if you want. These are really useful, and these say you can restrict what you want to count by how often it appears in all of the texts. So what this will say is I only want words that appear in one document out of all of the documents at minimum, or maximum I want words that appear in 100% of the documents. I can also say, show me the words that, show me only the top 100 most frequent words here. Or I could say, only show me these words. Or I could say, don't show me how often they appear, but show me just only whether they appear. So if you turn on binary, it says it will only say 0 or 1 if it appears or if it doesn't appear. So you can see this is kind of like a Swiss Army knife of a lot of the techniques that we've been using so far. So it by default it lowercases things. By default it tokenizes words. It does a lot of the stuff that we've been doing already. So why don't we run it on our Gutenberg corpus? So why don't we have it do all of the tokenization and everything? So we can make, if we take the NLTK corpus Gutenberg raw function, and we give it all of the file IDs. Yeah, maybe we could put this in a list. Yeah, why don't we try it with just one first? So this is leaves of grass. And if we were to do that, it just gives us the raw text of leaves of grass. Whitman raw is that raw text. And now if we run Scikit-Learn feature extraction text count vectorizer on Whitman raw, let's see what it does. Okay. I can call this Whitman vectors if I want. Yeah, and so it shows me, it doesn't show me a whole lot. Because just the default view for that object it shows me that it hasn't really done anything yet. So to get this to work in Scikit-Learn, the terminology that it uses are fit the model and transform the model. Oh, right. But fit transform is the one that actually takes the documents. So we should be able to run this. Right, yeah. So it doesn't like just one document. It wants a list of documents. And so if we give it a list with just that one in it, okay, now we can see what's going on. Okay, so it tells it's a sparse matrix in compressed sparse row format. Okay, so what this means is it's just like a pandas data frame, only it's just chosen not to take up the to take up the computer's memory with all of the zeros and other things that it is keeping track of. So if we wanted to take a look at this, we would first have to convert it to a dense matrix. Is it too dense? Yeah, too dense with no underscore. So, yeah. So what you're seeing here is a list of lists. And the first list and the only list that it contains is just all of the counts of Whitman here. Now, the crazy thing is Scikit-Learn has stored the names of all of the words in a different place entirely. So we have to write this slightly differently. So yeah, first I have to initialize this vectorizer before I fit and transform it. And then that will get me something, I think it's called feature names. And I think it comes from the vectorizer. Yeah, so get feature names is the one that I have to use. So yeah, it's alphabetized them, but yeah, these are all of the words in Whitman. So I could call this Whitman words, and I can call this Whitman counts. And I can put these together into a pandas series or something if I wanted to by zipping them. Okay, yeah, that didn't quite work the way I expected. Yeah, do I need to do this the other way around? Yeah, maybe I can do it as a dictionary comprehension. So I can say word count for word and count in zip, Whitman words, and Whitman counts. Yeah, maybe this needs to be a data frame. Let's try the simpler version first. I see. Yeah, because it thinks this is a matrix with one row. And what can we do with this matrix? Okay, live debugging. All right, yeah. So let's look back at this. So I bet I can make a data frame with just Whitman counts, but then I have to pass an index. Or I could pass the columns. Yeah, okay, so yeah, this is exactly it. So we have, in other words, a matrix of one row, and this row indicates that we're dealing with one text. That's Whitman, and I've given it these columns here, column headings, which just represents the names of all of those words. Otherwise, they'd just be counts. So, with one text, this is not super exciting, but it's really exciting. I mean, it's really powerful. You can see when we run this on a large number of texts, because it does the work of tokenizing and aligning all of the counts from all of the text all at the same time. Okay, so I'm going to copy this and paste it down here, and I'm going to copy and paste it down here, but instead of just dealing with Whitman, I'm going to deal with a list of texts. So yeah, what is my list of texts going to be? I think Gutenberg raw is yeah, I don't think I defined that yet. Okay, so I want, instead of dealing with a dictionary, I can deal with two lists. So one can be NLTK, corpus, Gutenberg, file IDs, and that's going to be our labels. And the other one can be just the text itself. So this is going to be a list of strings. So it's going to be the raw version for that file ID. So what this does is it just goes through each of the file IDs that I'm giving it from this list, and it gets the raw text for each one. Now, just some checks. How many do I have? I have 18 texts. Good. Yeah, what if I were to just look at this? Yep, that's the text of Emma. Great, that's precisely what I want. So this is the kind of thing that Scikit-Learn likes to fit and transform. So if I were to run vectorizer fit transform on this, after initializing that object, then this should do a lot of cool stuff all at the same time. So I'll call this Gutenberg vex for vectors. And why don't I just make that dense right away? Yeah, so this is going to be a matrix, and the shape of that matrix, in other words, the rows and columns are going to be, it's 18 rows, or yeah, is it 18 columns, and 42,000 something words. So that's what we're dealing with. And I can put this into a data frame. And you can see this is just the raw counts of all of the tokens in all of these files. So we have 18 rows here starting at 0. Each one of these rows is a text. And each of these numbers is how often that particular token occurs. Now these tokens don't have labels by default, so we have to tell it what the labels are. So we have to say, okay, these columns are actually vectorizer get feature names. Yeah, so Zuriel is one of the angels or one of the demons in Paradise Lost. And so, yeah, it doesn't surprise me that it only occurs in one text. So this one is almost certainly Paradise Lost. And some of these other ones are also angel and demon names. Great. So columns as feature names, and because we have kept track of the file IDs up here, I can pass that as an index. And you see that gives us labels for everything. So I can call this Gutenberg counts. Great, so I could do the same thing as before, where I can compare some of these values, I can plot some of these values. It's just I've done it all much faster than before. So yeah, it's almost strange that we learn to do all of this stuff like tokenization and lowercasing everything first, when there is this library that can do it all for you. But the reason is that, as you've seen, tokenization has lots of quirks to it, and what we call a token is different depending on the kinds of things that we're interested in studying. So again, we could take this and we could divide it by the lengths, but this might not work the way we want by default. because we have a version here, Gutenberg counts as actually transposed from what it was before. So if we transpose it again, now we have all of these counts as columns. Now it's a lot easier for us to calculate those lengths. Calculate the frequencies, that is. Yeah, and we could assign that. I think I already used that. Yeah, now we can look at the frequencies of particular words. So angel, of course, appears a lot in Milton, a lot in Sarah Bryant's short stories for children. Surprisingly, not that much in the Bible. But yeah, why don't we plot this so we can see it better? So maybe I have a hypothesis here that the word angel occurs way more in older texts than it does in newer texts. So because we have these texts that are all in this regular format where it includes the date, I bet we can extract the date from those. So we can write a little function to go through and get the date. Yeah, and why don't we make it part of this file ID? So we have this thing already called Gutenberg texts, and it's a list of all of the strings. So we're going to use that, but we're going to write a function, and all it does is it goes through all of the tokens and it finds the first numeric token. So for each token in those tokens, if the token is numeric, is it isnum? It's is digit is numeric. If token is numeric, return that token. And that's all it's going to do. Okay, so we have a list of tokens, I think, already somewhere. Yeah, I don't know. What did we call it? Did we call it like Gutenberg words? Oh, weird. But yeah, that's no big deal. We can just make that really quick. So this is going to be a list of all of the tokens from all of these texts. So NLTK corpus Gutenberg words for a file ID for each file ID in... Actually, we already have this file IDs. I'm gonna just peek at that. Yeah, so it's a list of all of the tokens for all of the texts. Okay, so for each one of these, we want to go and get the date. And make this a new list. Great. I love that for the Bible, it's inferred that 1 is the date. And I wonder which one this is. So it's not working for all of them, but it does an okay job. So why don't we prepin this to the file IDs? Because then we're going to use the file IDs when we create this data frame, and then maybe it'll sort, maybe there's a way to sort according to those file IDs then. All right. So file IDs with dates, maybe I can call it date file IDs. So date plus file ID for, I'm going to zip together dates and file IDs. Great, yeah, that's pretty much what I want, but how about I add something in there? So maybe I can make this an F string, actually, and just say date file ID. Okay, so that one's not quite working, but yeah, already this is kind of useful because it will give us an idea about how frequency of certain words changes over time. Yeah, so what if we were to run this same thing again? But instead of giving it file IDs, I'm going to give it date file IDs. Great. So what if I were to look at, why don't we transpose that and get angel out of it? Wow, just as raw counts, it appears a whole lot in the Bible. Yeah, more than I thought, actually. Yeah, what if we were to sort this? I can call this angel counts for now. Yeah, so we can sort the index. So that effectively is sort of sorts it by time of publication, almost. Now if we plot that as a bar chart, in fact, because it's kind of continuous now because we're dealing with time, we're dealing with dates, it does kind of seem that the earlier the text is, the more likely it is to have the word angel in it. What about a word like thou? Let's plot what that looks like over time. Yeah, again, yeah, much higher the earlier you get. What about thee? Yeah, again, in Blake and in Whitman, because Whitman kind of uses slightly archaic language. So yeah, if you're interested in how words change over time, this is one thing that you could do. Great. Yeah, so why don't we stop here for now, and tomorrow we'll talk more about TF, IDF, and we'll get into some of the other scikit-learn functions. But yeah, I'd encourage you to play around with this on your own and to try a few different corpora if you want. So there's the inaugural address corpus that's in the NLTK, but yeah, you can also use a corpus of your own design. All right, looking forward to talking to you more about this later.